Hi guys, today I'd like to briefly talk about an effective force that everyone is aware of and that allows us to, let's say, um, modify slightly the idea that F equal m per a will be still okay. But when we discuss about free falling object from the sky, suppose a stone, uh, and this there is no air. We always said no air because we didn't want to have frictions as a contribution to the force, and this would lead into the equation that m times g is equal to m times a, and then in effect the mass simplifies and you don't have to care about the mass in those situations. Okay, in everyday's situation it's very hard to get rid of hair, for example. So there'll always be some effect about frictions and turbulence in there. But even more, I'd like to give you an example where we replace air with something different, which we're very familiar with, which is water. So let's float our object in water. Okay. Uh, so let's see water. And for the aficionados HO2 with anything just water inside. Okay, this is still an idealized version because we all know that in water there are many other elements dissolved, but let's keep it simple and easy. Okay, so this time we can, and let's see what happened to the free falling situation. I won't go too much details for the throwing object in water because that's fluid dynamics, and I have no idea about fluid dynamics. I know I will just link the equation for like Bernoulli's equation and things, Navier-Stokes equation just for reference, but I'm not going to deal with that. I never did. It takes quite a lot of study to get a hang on those equations. So I will just do a simple example: floating object and object falling into water without too many decoration on it. So this time our scientist, or not scientist, our whatever guy is on the bottom of the sea. This is the sea level. Okay, nice. And of course this time he will need the mask because and the oxygen as well. Not because there is no air, but because we are underwater. Okay, nice. So still this guy needs the mask and is still with his stone in hand. He's happy with his stone and he never get bored with the stone. So let's see what happens. So how can I say? So we know that um, okay. So I will. So the idea is that um, molecules, okay, from of water from all around the places, okay, bump. So they move. So I can do a zoom. So this is the stone, and these are the molecules of water, okay, and they go and bump towards the stone. They scatter off in every direction, okay, and this continuous moving particle will create and of course there is will create an average force, okay, directed in some direction. So first of all we remember that the force of gravity is still acting, so F equal mg mg. Well, now we always remember that g is the small g, not the big G. So it's mass of Earth g r square. Now we're in the bottom of the sea, so r square is slightly different from the crust, but that's okay. Still 9.81, let's say, for easy of calculation, meter per second square. Okay, now we need to remember that F equal ma is one of the three principles that Newton's discovered in the 19th centuries. And the other one of the other principle is that when you exert a force onto something, that something will exert a similar force back to you. Okay, so there is kind of reaction to your force. So somehow there must be a force that is going upwards in this situation. Okay, and the amount of this force is in this situation is given by this simple formula. So let's say there is an upward force, which we call force A, Archimedean force, because the history goes that this scientist, Greek philosophers as well, was floating in water, and then he realized that the reason why he was floating in water, not sinking, was because there was a push given by the water to his body, upwards push, and this push was somehow proportional to the amount of liquid that this body would move. Having said in other words, so think about, we need to explore two concepts, density and volume. Sorry, but first let's make another picture. So we have a stone made of water now, the same volume, but the material is water. So imagine in water to create a boundary. It's the size of the stone, and then enclosed in this boundary there is just water. Okay, it's not complicated to understand that in this case mg will be equal to Fa. Why is that? Because there is no reason why a bowl of water would sink, would be on average stay in the same position. Okay, of course this is an extreme simplification, because we all know that water can be hot and cold, and if it's hot and cold, we all know that there could be some turbulence or some movement of water due to thermodynamic behavior. So the water flows, and we all know that because at the seaside, in the oceans, there are let's say streams of heat that flows back and forth between the seas and change the temperature in the water, and so on and so forth. So allow me to forget about thermodynamics, migration of water from hot and cold. Let's keep it easy. So suppose you have a glass of water. In a glass of water, I don't expect to see much thunderstorms or or things like that. So let's suppose that this blob of water stays in constant floating. So F equal ma. Now, what is the difference when we replace the material? Okay, so how do we, first of all, how do we replace m in if we call this Fa? How do we replace m in this equation? Okay, so the idea is simple. We need to introduce a concept and it is called density. Density is in unit of measure is kilograms over meter cube. Okay, what that means? Meter cube. And what does density means? So let's forget about this one and now think about for a second a cube. I can do a sphere, but let's pick a cube. Okay, and this cube is 1 meter square, cube, exactly. It's a cube with the sizes, or it's not well drawn, sorry, but suppose it was well drawn and all the sides are equal in length, and this is 1 meter. So 1 meter, this is 1 meter, and what else? And this is 1 meter. So in x and y, okay, so we all know that the volume is 1 meter cube, because the volume is the product of L times L times L, which is a cube, and the units of measure carries over accordingly. Okay, so this is the volume. Okay, now think about filling the volume with balls, tiny balls. Okay, and we can put, let's say we put them in order, and these balls could be thought as particles, molecules, atoms, or, well, particle, atoms, molecules, whatever. It doesn't really matter for the moment, as long as we, for important thing for this calculation is that these balls are as big as or as small as, in order to have the same qualities. So they must be of the same kind, roughly. So you want to talk about density of water, for example, density of an element, for example, density of metal, like iron, things like that. So density of air, we all know that is not made of one particular element, but if the air is roughly of the same kind, you can calculate an average density, and you have these molecules of air, okay, which comprises of all the statistical mixture or whatever it's in the air. It could be a matter of water. If the water is salty, there will be salt in it, dissolved, and other stuff. If you think about a block of iron, the density of iron is simply the number of atoms of iron per meter cube. So, okay. So what is the density? So basically, the density represents the number of these dots present in the meter square. And why is this important? Because, and how is it related to the mass? So the mass will be easily represented as density, which is rho. Rho, it's a Greek letter. I don't know if I wrote it correct nicely, but if you're not familiar with, you can check it. Rho times volume. Okay, rho times volume is mass. It's always like that. If you think about the kilograms over meter cube times meter cube. Meter cubes goes away and you're left with kilograms, which is mass. So as you can see, the mass of an object can be thought as technically an integral, but let's say a sum or just a multiplication, if you have one material, of the density times the volume. And of course, if you have, this is important because if you think about a block of, let's say, iron, and a block of, let's say, oxygen, air, yeah, so you would expect a block of iron to be heavier of a block of air, of course, because if you think about it, Otherwise we will be crushed on ground completely by the weight of the air above us. Okay. Instead, there are so so less molecules of oxygen in the same block. So I can do this, for example. I'm exaggerating because I don't know what's the proportion. I should have checked that. But allow me to do simplification. So there's one here, one here, one here, one here, one here, one here. Let's say 6. As you can see, if you think about, and these molecules, by the way, or atoms, could be freely moving in this block. It doesn't matter. It doesn't have to be. It could be an average over time. It could be something fixed and static. If it's a crystalline structure, it doesn't really matter. I mean, the concept applies in many situations. The idea is that you have many more purple, many more. I don't know how many, but let's do a big pile of purple that we count, and way less orange one. Okay. in the same space. So therefore, we can see that this block of 1 meter square will weight less if it's made of oxygen, for example, or iron. And I don't remember the root formula for ferrum. I don't remember how many atom consists a molecule of ferrum, but let's say Fe for easiness. Okay, so this is the concept of density, and now you can kind of guess why in this situation down here, where we have, let's say we put another ball, different color, we put this one, and now there are 3 situations, right? This situation where suppose Fa is less than mg, Fa is equal mg, and Fa is bigger than mg. Why this can happen? Because basically, if you replace mg equal to rho v yes, Fa equal rho vg, yes, you can see that so rho v a, acceleration a, right? The acceleration a is now it's not exactly g, right? It's not exactly g, because rho v doesn't cancel out completely with m, unless in this case here where the mass of the liquid is exactly the same mass of the ball, because it's the same density. So we have that A is equal to G times rho V, rho V. Okay. And if this, M. Okay. And this ratio here can be bigger than 1, equal 1, or lower than 1 in these 3 occasions. And this, it depends on the density of the material. If the density is much higher, meaning that the mass occupied by the object is larger than the mass that would be if it were water, this force is pushing upwards. So sorry, this force is pushing always upward, but is less intense than the force of gravity. Therefore, the ball is sinking, and this would happen, for example, with iron, block of iron in water. I think you wouldn't be surprised if you would see a ball of iron sinking in water. Now, wood, for example, float easily because the density is less than water. And in this case, this ratio is bigger than 1. The acceleration is larger than g, so you go up. So the ball can go up with an acceleration of this amount. Okay. Now, as before finishing off, I want to just remind you that this is, no offense, but of course you need to be smart about it, because we all know that iron is very dense, and then if you have a ball of ions, that will sink. But we also know that there are big, ginormous boats and ships that do not sink unless they're broken. So why is that? Again, they're made of iron or other metallic materials. Maybe not iron, but let's say iron for simplicity. There were some iron somewhere at some point in ships. Okay, so suppose a ball of iron, and now think about the ball made of shields, shells actually, shells because it's a 3D ball. Okay, shells, and then you can think about shells, and then if you had the possibility to remove, they're all made of iron, okay, but you leave some you can put air if you like, air, you can leave a hole, and in the hole you remove iron and you replace it with air, so it's a hole in the ball. Of course, this would, and then you can think about another very extreme case where you have basically a very, very tiny shell on the surface, like a crust made of iron, for example, and all the rest is air, as opposed to the full iron ball. Okay, as you can imagine, this three situation will have a different density. Why is that? Because the density is, in fact, it's a derivative. First of all, we all know what the derivative is. So rho is the derivative of mass over volume. Yes, meaning that how does the mass change with respect to the volume, and also this means that the density is a field in some sense, so it depends on the coordinate x. It could be, as you can see, it could be high here, very high, and very low here. And on average, when you want to calculate the amount of force that a fluid, let's think water, but also fluid, other fluids, think about other fluids, it doesn't have to be water, but any fluid will exert this kind of push. In fact, even air, which is a gas, but under certain conditions behave like a fluid, so it exerts some push upwards. But this is, as I said, fluid dynamics. It's a bit more complicated. I'm not an expert at all, so I don't want to mess up with it. But just to give you an idea that this consideration takes place when you have to design a boat, a projectile, a ship, a plane, maybe even definitely even a satellite. Even though there is no air in space, at some point they have to go through the atmospheres. So anyway, I'm always forgetting about this because I never studied those things, so I'm not an expert. But you can look it if you want. What I want to say is that rho is a field, meaning that in each point you have a map that tells you how high is the density. And those three objects could well, and you could well make an object like a ball that would float in water, right? So you can suppose I draw this, cancel this one. We know that density depends on the position inside the object that you are calculating density of. We know that, and also we can forget about this one. Suppose we have these three situations. We can safely think about that. Oh, I canceled the water as well. Let me just place back our seaside level. Right, so we know that this ball would float, most likely. If you do the calculation right, I'm sure that you can find the thickness of this shell such that delta x such that the density times volume is less than the mass of water in the same volume. Okay, and this would be floating, and then you can on top of water. Then you would have an intermediate situation or a bit thicker ball. In this case, it would be floating but not sinking, so there would be at equilibrium, let's say. Okay, so Fa equal Fmg, so there is the net force is 0, so it would stay there. And then there would be a third case. I'm assuming that there is no chance, maybe I'm wrong, but suppose that there is no chance that for a ball of iron not to sink, and then this would be where Fa is less than mg, and then they would have an acceleration downwards that would move, basically. So what I'm saying is that Fe, of course, would have an acceleration that make it move upwards, and then it stays on top of the water because there is no chance. I will tell you why. There is no, I mean, you need extra force to escape the atmosphere, right? So but we can do this calculation another time. What's forcing the amount of energy necessary to escape the atmosphere, for example. This is not the case because there is no force. There is just a force of water that stops when you are out of the water, and therefore the ball of iron would stop there and float on top of the surface. Okay, so now our happy scientist here knows how to design a floating ball of iron if it's necessary, and he can do some calculation to understand what's the time it takes to reach the ground in water, okay, which would be, I think, very similar to the the formula that we derived last time, where we replace mass with rho g. No, sorry, where we replace acceleration with sorry, I got this wrong. Well, where you replace acceleration with this formula down there, which is a bit more complicated, but still manageable. Okay, so I hope this makes sense. If not, give me some comments or questions, and see you next time. So I want to do one more like classical physics, or maybe already next time I would like to introduce some quantum mechanics, some easy stuff just to give you an idea of what it is, and then I would alternate between some classical mechanics and quantum mechanics, because to be honest, there are not very many things on quantum mechanics that are easy to grasp, and I'm not super familiar with all the. I mean, it's not easy to basically give a simple example for quantum mechanics, but at least the one that I can, I would like to post them. So stay tuned. There will be some quantum mechanics soon, but this was just a video to complete the effort of our scientists with the stones and bolts and trajectories. Okay, have a good day and see you next time.